Hey everyone, welcome to today's GRE Prep Hour. I'm your host, Tyler. I am an instructor with Manhattan Prep. And today we're going to be talking about counting/combinatorics. Both those topics kind of refer to the same thing. And one thing I want to say off the bat, when it comes to counting/combinatorics, this is one of the hardest question types you'll see on the entire exam. But the good news is it is relatively rare. So I would expect you would see no more than 3 of these on a single test. And it's important to realize this is not something that you want to go hard into, right? Like this should be one of the final things you study, if at all. So before you start pouring hours into this, which is a difficult topic to master, you want to make sure that you're very comfortable with exponents and geometry and number properties and all the other aspects of the quantitative section that you're more likely to see. That said, I enjoy this stuff because it is so difficult, so I'm excited to talk about it with y'all here today. And if you're here live in the room right now, this will also be recorded and uploaded to YouTube later. But if you're live here on Zoom, why don't you go ahead and chat to me where in the world you're located? I'm currently joining from San Francisco, California. It's a nice sunny day out there. All right, we got some New Yorkers. I used to live in Brooklyn. I moved back to California about 2 months ago. Got some other Californians as well. So yeah, it looks like we got East Coast and West Coast. North Louisiana, we got the South in here as well. All right, well, welcome. Let's go ahead and start with an introduction to combinatorics here. And I want you all to go ahead and read this question. And I'm going to walk through the solution with y'all together. And first thing, when it comes to these counting questions, what you don't want to try and do is manually count the stuff up on your fingers, any manual approach like that, like pant one, shirt one, hat one, and then pant one, shirt one, hat two. That's going to take way too much time. Instead, I like to imagine combinatorics as these branching possibilities. So for this first pants decision, we have 5 potential options there. And then each one of those pants options is going to have 4 branching shirt options. And then each one of those shirt options is also going to have 2 hat options branching off of that. And then with those numbers, you apply what is known as the fundamental counting principle. You just multiply those numbers together, and that produces your outfit total. Or visualized, if you want to see like the full map of all those branching possibilities, it would look something like this. So let's take that idea and start to complicate things a little bit more. And I want to introduce a method here, something called the slot method. That is my personal favorite way to approach counting questions. So go ahead and read this problem. And again, we're going to walk through this one together. And the way the slot method works is you want to begin by just drawing a line, a slot for every decision that's being made. And in this example, Jane is picking 3 people. So I'm going to draw 3 slots. The second step is you want to label each of those slots. In this example, we have an assigner, a summarizer, and a host. So I'm going to label them A, S, and H. Third step is we're going to populate those slots from our selection pool. So we have a group of 9 friends that we're starting with. So my first choice, I have 9 people, and then it's going to be reduced every time I make a selection from that pool. So I have 9, 8, and 7. And then applying that fundamental counting principle, you're just going to multiply those numbers together. So here we'd have 504 potential combinations. However, there is an optional 4th step you might have to take depending on the setup of the problem. In this version, the way it's written right now, we're done. The answer is 504. But if I rewrote this problem and removed the assigner, the summarizer, and the host, read this new example now. So here, everyone is just a member on equal footing. There's nothing distinguishing the members of this group. They're all equal. When that happens, when any of my labels match, right now I have M, M, and M, member, member, member. When that happens, we have to take an extra step of division. Let me explain why. In the original version of this problem, when I still had the assigner, summarizer, and host, say I ended up picking these three friends, Amit, Liz, and Mikkel, there are 6 different ways I could kind of swap their positions and permute them around to get, 6 different orderings that are unique in the original wording of this problem. But if I take the roles of assigner, summarizer, and host away, I've overcounted by 6. Only one of these should be adding to my count in this new version of the problem. So the fourth step you have to take when you have matching labels is you need to divide by the factorial of identical labels. And if you are unfamiliar, a factorial is written with an exclamation point, and it means you multiply by that number by every integer down to 1. So 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. So I have 3 matching m's. That means I need to divide by 3 factorial. So we went from 504 down to 84. So when you're in a situation where shuffling positions does not increase the count, you're always going to divide because your total count is then going to be smaller if changing positions doesn't mean we get a new count. So I know that was kind of a lot, but to recap, here's the process one more time. First step, you draw a slot for every decision being made. Second thing you want to do is label each of those slots. If every label is unique, then all you have to do is populate those slots from your pools and multiply, and you're done. However, if, depending on the problem, you have slots with matching labels, then not only are you going to populate those slots, but you also have to divide by the factorial of matching labels. And then you're done. And if you're already a bit familiar with permutations and combinations, you might also know these formula on the screen right now. And if you prefer to do it that way, that's fine. There's nothing wrong with these formulas. In my opinion, I think using the slot method is a little bit easier the first time you're learning this, so that's my general recommendation. But yeah, if you prefer to do it this way, you're welcome to do it that way. The one modification I might suggest is for permuting, rather than memorize n factorial over n minus r factorial, in my head, it's a little bit easier to conceptualize it as the first r terms of n factorial, right? So for 9 permute 3, I'm just taking the first 3 terms of 9 factorial, 9 times 8 times 7. Similarly, for combinations n choose r, rather than this whole formula here, I like to think of it as the first r terms of n factorial divided by r factorial. So 9 choose 3, I'm taking the first 3 members of 9 factorial, and then I divide it by r factorial. And for me, I just find that that kind of cleans up this long cancellation step and gets me to the answer a little bit faster. Okay, so now I'm going to give you all a real problem to do. I'll give you about 3 minutes here. And as you figure out the answer, please chat it to me. Here you go. All right, let's check out the solution to this one. So our coach here is selecting 5 players. So I want to have 5 slots. And in terms of the labels here, every player is just a teammate. So I use T right there. There's nothing distinguishing any of these selections from one another. And our pool is 9 people, so I'm going to start with 9 and decrease that until my last slot. So I'm going to multiply that numerator, but I also need to divide by 5 factorial to account for the 5 matching T's. And when I get to this step here, make sure you simplify before you try and cram all that into a calculator, because there's going to be lots of opportunities to cancel items in the numerator with items in the denominator. So if I do something like that, the math essentially becomes 9 times 2 times 7, which is 126, choice D. Now I want to stick on this problem, but I'm going to change the rules a little bit. So instead of 5 basketball players, what if this coach were selecting 4 players and 1 captain? Try out that new version of the problem, and we'll treat this like a fill in the box. So the answer won't be any of these down here. So what's changed here is going to be with my labels, because instead of 5 identical T's, one of these T's should now be a C for captain. But nothing's changed about the pool. We still have a set of 9 people, so that's still going to be 98765. But instead of dividing by 5 factorial, I only need to divide by 4 factorial, because there's 4 matching T's now. So compared to the original version of the problem, I'm dividing by 1 less 5 than I originally had, So the answer is going to be 5 times higher than 126, which is 630. And we're going to do one more riff on this problem before we move on to something else. So let's change the rules one more time. What if this coach were selecting 3 regular players and 2 co-captains? Chat me what the new answer would be. Sorry, I was muted. This new example is going to affect our labels once again, because now instead of a single C, we've got 2 co-captains. So I've got 2 C's and 3 T's, and each of those gets its own factorial. So we need to divide by a 2 factorial for the captains, and then a 3 factorial for the teammates. So the 3 factorial is kind of already there. And then instead of dividing by a 4, that should be a 2. So compared with the previous answer of 630, I'm now dividing by 2 instead of a 4, so it's going to be twice as high. And the answer to this new setup would be 1,260. Okay, we're going to move on. I'm going to give you a new example to try next. Give this one a shot. So as I mentioned in the hint there, Liz is making 6 decisions. Specifically, she'll be selecting 3 shirts, 2 pants, and 1 pair of boots. But you have to keep in mind that each one of those decisions has a separate pool, because the shirts are coming from a pool of 7, and the pants are coming from a pool of 5, and the boots are coming from a pool of 2. And in terms of matching labels, we have 3 factorial coming from the shirts, 2 factorial coming from the pants. Technically a 1 factorial from the boots, but 1 factorial is just 1, so you don't have to worry too much about that. And as always, make sure you take those opportunities to cancel items from the numerator and denominator, and ultimately your answer should be 700. Moving on. This next problem introduces a new scenario that we haven't checked out yet. But before I say anything further, I'm just going to throw you all into the deep end to see if you can figure it out. So this one's pretty tricky. I think it stumped a lot of y'all. Let's break it down. So there are ultimately 8 different decisions. We've got our choice of meat, and then these 7 condiments: lettuce, tomato, pickle, onion, ketchup, mustard, special sauce. And meat is the more straightforward one. There's 3 options. You got to choose one of those. But then for each of these condiments, we can have as many or as few as we want. So for a decision like that, it's essentially a yes or no for each of those 7, right? If our only options are yes or no, that's a pool of 2 for every one of those blanks. So looking at the answers, you can tell we've got a whole bunch of 2s there. We're going to need that 2 to the 7th. And given that there's 3 meats, that means the answer is E, 3 times 2 to the 7th. So the kind of new rule here is if you see one of these binary decisions, something where the answer is just yes, include this, or no, don't include that, that's going to be a power of 2. Another implementation. Okay, so I had a question before I move on. A question that just came up was, how come meat is just 3 and not 3 times 2 times 1? And the answer is because you must include meat, right? No matter what, a burger has to have meat in it, and we have 3 different options. So that's a pool of 3. So according to the fundamental counting principle, we're just multiplying by 3. It would be more like 3 times 2 times 1 if you got to include 3 different meat options on your burger. So like you get the chicken and the burger and the fish. Um, but even then, yeah, like 3 times 2 times 1 is overkill for what we have here. We're just picking 1 from a set of 3. Another question I had in the chat, is there a reason to use the formulas over the slot method? Um, the only reason I would say is if you're more comfortable with the formulas, and every test taker, every individual is always going to be unique in some respect. So part of this is just experimenting on your own. Try problems no matter what they are, try them a few different ways and figure out what solution methods jive best with your own personal learning style. So if you prefer the formula, if that's easier for you, stick with that. If you like this new slot method, keep going that direction. Okay. So I want to move ahead. Another kind of common implementation I see with counting questions is with words and anagrams. And if you're unfamiliar, an anagram is just a rearrangement of the letters in a word. So let's take a look at this problem. I'll give you a couple minutes. Chat me what you think the answer is. So if you want to apply the slot method here, there's going to be 11 decisions for those 11 letters that we have. And in terms of the labels, think about the composition of those letters. There are 4 I's, 4 S's, 2 P's, and a single M. And we're using every single letter, so basically we're getting 11 factorial on top. The 4 I's mean we divide by a 4 factorial. The 4 S's mean divide by another 4 factorial. And the 2 P's create a 2 factorial there. And that's going to match answer choice E. So that's one way to look at it if you want to apply the slot technique there. But when it comes to anagrams in general, just because they're, a common form you might see for this question, if you prefer, you can just recognize anytime there's an anagram, the answer is going to be the number of letters factorial divided by repeated letters factorial. And that might be a little faster than drawing out 11 slots like you're doing here. And anytime I've seen this come up on the GRE, it's always using the exact same amount of letters. If I could have like 10 letter and 9 letter and 8 letter, this question becomes really complicated, but I haven't seen that show up on a test. So I'd anticipate if you ever see anything like this, it will be the exact same number of letters. And that's what makes this rule work. So let's look at a pretty sneaky one next. This one's very challenging. And that's all I'll say for now. So one potential route I have from A to B, if I can only move right or up, would be to move right 3 times and then up 3 times. Or I could do the opposite. I can move up 3 times and then right 3 times. Or I could have a route that looks like this, where I am going upright, upright, upright. But you will see every single solution is going to have this spelling of 3 right moves and 3 up moves. In other words, every potential solution is an anagram of this word RRRUUU. So applying my anagram logic, the number of letters here, we have 6 of them. So I have 6 factorial in my numerator. And then my repeats, I have 3 U's and 3 R's. So I should divide by 3 factorial and another 3 factorial. So one of those cancels cleanly. I can cancel that 3 and 2 with that 6. And the answer is just 5 times 4, which is 20. Again, very challenging, but on a really hard problem, you might see an anagram type of question hidden in disguise, kind of buried underneath this complicated story. But at its core, it's just rearranging R's and U's, our right moves and our up moves. One other piece of logic. This next problem involves something called a subset. So a subset just means you can't have any repeated values. Every item must be unique. Try it out. So if I start this one with the slot method, quantity A, I'm making 3 decisions, and everything is on the same level. Nothing is distinguishing those 3 decisions. They're all just members of a subset. And my pool is 6 options, so I have 6, 5, 4. I need to divide that by 3 factorial from my matching m's. So that 3 and 2 cancels with that 6. And I would get 20 for quantity A. For quantity B, this time I have 4 labels. So I'm going to have 6, 5, 4, 3. And then I divide by a 4 factorial here. And the fact that I'm dividing by more is actually going to make quantity B smaller. And we're only going to get 15 there. So quantity A is the bigger value. So A is our correct answer. And let's revisit this one for a second. If I change the setup here, if instead of a 3-member subset, what if I had a 2-member subset? Does our answer change? Chat me what you think. So if we had a 2-member subset, just filling in 2 slots, and then I divide all that by 2 factorial, because each of those have the same label. They're just going to be members again. So that's 30 divided by 2. We'd get a 15. So quantity A and quantity B would be equal in this case, making the answer C. And what I want to point out here is that combinations are symmetrical. So if I can use the kind of formula notation for a second, what I mean by that is 6 choose 0 is equal to 6 choose 6. The number of ways I can choose nothing is equal to the number of ways I can choose everything. There's one way to do that. Likewise, 6 choose 1 is equal to 6 choose 5. The number of ways I can pick one thing is equal to the number of ways I can exclude one thing. There's 6 different ways I could do that. And as we just saw here, 6 choose 2 and 6 choose 4, right? The pink notation and the blue notation. The number of ways to pick 2 things is equal to the number of ways to exclude 2 things. Both of those are 15. And then 6 choose 3, the original quantity A in green. That's the biggest it can ever be. Right? When you're at the midpoint of that pool, that's as high as you can ever make a combination. So what if I had a total pool of 9? Which is bigger, 9 choose 4 or 9 choose 5? Yeah, and I'm being sneaky there. Neither is bigger, they're equal because it's going to be symmetrical. The choose 0 and the choose 9 are equal, and then they meet in the midpoint. 9 choose 4, and 9 choose 5 are the same value. So let me ask you something pretty tricky. What would be the value of 17 choose 16? Which sounds scary on its face, but if you apply logic, you can figure out what that would be. What is 17 choose 16? It's going to be the same as 17 choose 1. The number of ways to pick one thing from 17 is equal to the number of ways to exclude one thing from 17. The answer is just 17. And to put that into a more kind of generalized formulaic approach, n choose 0 and n choose n are always going to be 1. N choose 1 and n choose 1 less than n itself is always going to be equal to n. And I know that's kind of like a mouthful of algebra, but some of you like the hard-coded algebraic rules like that, and that's how it works for combinations. One last thing I want to say before I show you this next problem is an alternate way of writing combinations. Like 6 choose 3 is equal to 20. A notation you might see on the GRE is just two numbers written above each other in parentheses. So if there's no fraction bar, it's just a number on top of another number like that. That's the same thing as a combination. It's the same notation as 6 choose 3. Which in turn is kind of the same logic we use down here with the slot method. So all of that in green, it's just different ways of writing the same thing. So let me show you today's final problem. It's going to be kind of a doozy. But I think if you apply some logic and look at the answer choices, you may be able to figure it out. Here you go. So I think rather than try to build this one up manually, where I'd like to start here is just looking at each of these answer choices and recognizing that by definition, probability is my desired outcomes divided by my total outcomes. So speaking more specifically to that, the total outcomes, that's going to be the number of ways I could pick any 5 coins from 50. So it makes sense then that my denominator should be 50 choose 5, right? We're trying to find how many ways contain, what is it? One of the 5 coins being buffalo nickel. Out of all the different ways, I could pick 5 coins from 50. So my denominator must be 50 choose 5. So already we've got it down to a 50-50. And then think about what's going on in the numerator. See 50 choose 3. That's the number of ways you can pick 3 coins from 50, which is kind of oversimplifying what we're looking at. What I have here, 3 choose 1. If I only want one of the coins to be a buffalo nickel, then I must be choosing one of the 3 buffalo nickels. And then the other 4 are just the 47 unknown coins. So from the 3 that are buffalo nickels, I must pick 1. From the 47 that are not buffalo nickels, I must pick 4. And my probability is going to be that number out of the total ways to pick any 5 coins out of 50. So answer B is correct. All right, we're going to start wrapping up here to kind of walk you all through what I think are the biggest takeaways from this lesson. Number 1, don't forget about the slot method or and choose our formula if you prefer to do the formula way. But step 1 is always draw a slot for every decision that you make. Then you want to label each of those slots and then populate those slots from the pools and multiply. And then this 4th step is optional. If any labels match, you divide by a factorial for any matching labels. And as we just saw, combinations are symmetrical, right? The numbers of ways to pick nothing is the same as the number of ways to pick everything. The number of ways to pick one thing is the same as exclude one thing. And then it's always biggest at that halfway point when you're in the middle of the pool. And finally, in that last example, the nastiest combination problems you'll ever see on the GRE are these hybrids that also incorporate probability. But to tackle those, you just need to remember that probability is your desired outcomes divided by the total outcomes. All right, and that'll do it for today. Thank you all for being here live in the room, or if you're watching later on YouTube, hello to you as well. And one last thing I'll say, I'm popping a link into the Zoom chat there. I also teach courses for Manhattan Prep, and we open up session 1 of the course to the public. So if you want to just come as a trial student and check out what the course is like, you're welcome to do that. Please check out that link on the screen or on YouTube. There should be a link in the description as well. Likewise, if you enjoyed this prep hour, myself and my other colleagues also do a lot of these free workshops. So I believe that link is going to contain the future upcoming prep hours as well. So, come hang out again sometime, come check out a free class. Other than that, I hope you enjoyed your time today and I wish you the best. So I'm going to go ahead and close the recording.